part of my lectures about connecting different quantum worlds. And this time I want to basically talk about how to connect a photon to an atom or a spin. And the motivation behind there is a quantum repeater. And I will give the main emphasis this time will be just to show you a few examples of what you can do and what the limitations are. And also maybe mention what would be required if you really, build something with it. Yeah. So the question for from studying what is interesting physics to what we need to do that. And the examples I will give to see how far I will get. But I will give first something about this interfacing a single photon to an atom with various different ensembles like atomic ensembles or single atoms in cavities, and photons in ensembles from some dopants in crystals, which are solid state implementation of that. And in the end, if time, I will say a little bit about the problems of having things in a solid state with ensembles, and how you can maybe do that with a single spin or with two single spins, a nuclear spin and an electron spin. So the first thing is, why do we want quantum repeaters? You know that one of the big challenges if you want to send a quantum state of a very, very long distance is that the no cloning theorem basically prevents you to copy the state, which is good because that allows you to make cryptography or make secure communication. But it's bad because even the best fibers now, they have something like 22 or 30 kilometer is the loss length. So if you take a 100 kilometer fiber, you only get about if you have 0.2 dB per kilometer, you're at a 1% transmission over 100 kilometers. And even if you would have a 10 gigahertz source, you would only get a 1 hertz transmission over 500 kilometers and 0.01 hertz transmission over 600 kilometers. And so basically, 100 kilometers is something like the order of the limit where you can really send a quantum state over a fiber. Or you want to send, if you send it to air, if you send it to a satellite, it might be able to send it further. So the question is that if you can do, usually in regular communication, you have something that's called a repeater, where you copy your system, you amplify it, and you send it again. That's what quantum mechanics doesn't allow you to do. And there was a whole concept and ideas that came out of I think partly or most of it from Peter Zoller's group in this book, which had to do with how can you nevertheless implement something like a quantum repeater, and which also has to do that. Or anyway, what would be tools if you have something that is probabilistic in quantum mechanics, some operations that are probabilistic, to make them still scalable, to make them still that if the system gets larger and larger and larger, that it doesn't scale like exponential. I don't have much to say about the quantum cloning, that you cannot clone an unknown quantum state. The interesting thing is that the best quantum amplifier is basically a laser in that sense. If you can do that. So what was the idea behind building a quantum repeater? So when you start, you would have a very long decay length, a very long length where you want to send a signal. Usually in classic communications, you break it up. Send the signal to here, amplify it and send it again, amplify it, send it again. And therefore, you can get your signals through a very, very lossy channel. Now the idea is that you take these segments and make a repeat until success strategy for each segment. So that for each segment you establish entanglement between two nodes, between this node and this node, you establish entanglement. And here also you can do all of that in parallel. So typically it takes you a time to establish entanglement in each of these sections, which is typically in the order of establishing entanglement in one section. Whereas if you want to establish entanglement along this whole length here, it will take you an exponential amount of time compared to establishing a single section. Now, if we do that, now we have, quantum entanglement established in each of these nodes. You can take something that's called entanglement swapping by making a measurement on these two entangled particles, and then you can transfer the entanglement to these two ones, and then you can measure entanglement here again, and in the end, if you do that, you could get entanglement over the whole system. This was the idea behind this original paper by Hans Bruegel and Wolfgang Dürr, Ignatius Reactor, Peter Zoller, where they say basically the role of this imperfect local operations quantum communication. And if you can do that, if you make this repeat until success strategy, then you can get rid of this exponential scaling in a lossy channel. Now, what you really need for that is that you need to store your entanglement in the quantum memory here. Because you create this quantum memory, this is a probabilistic process. Here you create the entanglement again as a probabilistic process. But you want to have to be sure before you do your entanglement swapping here, that you have established them on both of them. So if you establish this earlier than the other one, in the probabilistic case, you have to store it. So you need, for that, you basically need a quantum memory. So you need, the important part to be able to do that is to have a quantum memory where you can install the quantum, this type of quantum states. Now, what is entanglement swapping? Entanglement swapping, I think, was the first time really discussed in this old paper by Marek Zukowski and Anton Zeilinger in 1993, and experimentally demonstrated in 1998, where basically it means that if you take two entangled states and you make a Bell state measurement in here, you can very easily see that if you take this psi minus state and a psi minus Bell state between AB and CD here and make a Bell state measurement, depending on the outcome of the Bell state measurement, you know what type of, you project A and D into an entangled state. And A and D never have ever interacted, and there was basically the paper behind Zukowski's original idea is that entangling systems that have never ever really interacted, never ever seen each other by this entanglement swapping. And you can take quantum repeater. The idea is that nothing else than taking many of those things together and putting them with a quantum memory. And for example, experiment where we showed in Heidelberg at that time that we can do that over many steps. That was this multi-stage entanglement swapping, 2008. Now this is one of the basic things to do. Now the next part was how to really implement that. And there comes a seminal paper by Lukin, Duan, Zerak, and Zoller in 2001, where they really made a protocol, which is now always called the VLCZ protocol, which is which tells you exactly what type of physical system you want to be able to do that. So the basic idea in the beginning was you take an atomic ensemble here, and you very quickly excite this atomic ensemble so that you have a very small probability of emitting a photon. And you take a second atomic ensemble and do the same thing. Yeah? And you make this excitation so weak that you never emit a photon on both sides. So if I detect a photon now on these beams, and you send these two photons on the beam splitter, and detecting a photon here on these detectors D and D bar projects A and B into the following entangled state, which is that photon came either from system A and no photon from system B, or there's a photon from system B and no photon from system A, and depending on if D and D prime defines the sign of this. Right? And of course, the other thing that goes in there is the phase of the photon as it travels along this path also goes in there as a phase of the in that system. Now, you now have established, so to speak, an entanglement between two atomic spin states here, and then you can read out the system by sending photons and making entanglement swapping, and thereby really entangling the gates A and D, and then you have entanglement between state A and state D, and then you could, in principle, you can have many of those, you can purify them, and you curate two photon entangled states, you can do whatever you want with entanglement between A and D, which is an entanglement between, which is a path-like entanglement. And so this was the original idea from Peter and from these four guys. So the question is that they basically, the interesting thing was that they really proposed a physical system that you can use, and these ensembles that interact with light, as I showed you in my first lecture. Now, this original one has some problem because if you do that over a very long distance, you have to keep these phases constant, and it's relatively difficult. And of course, it's possible, but it's difficult. And if you do the same thing, if there's a similar type of repeater, which goes virtually back to the virtual way of doing that with from Hans Briegel's earlier paper, where you really take make a two-photon Bell-stick measurement between a qubit, which is now a real qubit or not. So you have a polarization qubit here and a polarization qubit here, and entangle them. And this allows you, this makes it a much easier way to do that, because the path length here is not important. It's only important that the two wave packets overlap, because it's a homo-Mandel dip that you do here, and the other one is an interference experiment that you do. At the one time you have to have it stable up to the size of the wave of your photon packet. In the two-photon experiment, you have only to be stable on the size of the photon wave packet. On the one photon path, and then you have to be stable on the wavelength fraction of the wavelength of the light. So it's a two sets of really implementing this. This is the original proposal by Zoller, and this is basically in a way of how to implement the original proposal by Hans Briegel. Now, if you go to the math, and you find out that if you do these things, you can. Now the question is, how good are these repeaters? And there is a beautiful review from the group of Marc Nicolas Chizin, where all of this is worked out in detail. You don't have to look into this formula, but basically the frustrating end of this is you need very high efficiencies to break the things that you can do with a single photon if I send it along fiber. You have to be very good to be better than to do that. So you basically need very high efficiency. So if you show that, that's best shown in this graph, that he says, okay, this line A is what can I do with my best single photon source that I have. It's a 10 gigahertz single photon source, so I send 10 gigahertz, and I send it to my best fibers. Then my communication rate with just say 30 single photons is line A. And these other lines, you see that how long does it take to establish a single entangled pair over a certain distance with certain quantum repeater protocols. And this is all based on that you have a detection efficiency of the photons of 0.9 and a creation efficiency of that 0.9. These are very high. There's a memory efficiency of 0.9 and a detection efficiency of 0.9. Usually photon detectors in an experiment, if you do it in a photon experiment, you're happy if you detect 10%. Yeah? From the source to the detector. And these are very good experiments already. Yeah? Because this is not only the efficiency of the detector, this is the efficiency of everything, including the whole loop. Now, here you see that basically all these protocols, you have to go to very large lengths to these protocols start to be better, and then it takes you tens to hundreds of seconds to create one single entangled pair. Yeah? So it's a nice part, but what you learn from this review and this very thorough evaluation of Nicolas Chizin is that sometimes physics looks very simple if you put it down the basic principles, and if you try to put in the nitty-gritty details, things become extremely complicated. Much more complicated than you ever thought. Yeah? Because when you first, this was 10 years after the original paper. I remember when we discussed it in Innsbruck, these ideas, we basically thought, okay, this is solved. You can build these things, you do that, this was beautiful. You do that, then you will see the part. And when this came out, it turned out to be very tricky. You see that usually these memory efficiency you will see are best 0.8 what is achieved now in the experiment. And these photo detection efficiencies over everything to there are, if you work very hard, you may get up to 0.6 or 0.7. So these are very far away from really, if you want to implement a very long distance quantum communication link with a repeater, I think there's still lots and lots of work to be done and to understood how these things really, really work if you build a system together. Nevertheless,
do you see that there is any fundamental question, or is it just technical?
It's a question of that if you do.
I mean, by just technical, I don't need to be.
I think it's more than just technical. Sometimes it's that you make a proposal that is based on perfect detectors and perfect memory, and that might work really nice. But if you go an epsilon off, you might fall down a cliff.
So that would be more than technical.
I think it's more than technical. If you really build a large system, yeah.
So that's important to know that.
I think it's more than technical. I don't know. You have for the theorists here to think, but for me, it's like I think it's more than technical. If you need proposals. You need to think about things, to do things, which do not, rely on perfect operations. Yeah. Because everything, if you have to do perfect operations, you gain an enormous overhead, which may be probably. Well, that's my voice is getting out.
It's powerful.
Is it your? That's the speaker's signature. Okay. Nevertheless, these are things that you're always happy to know after you study your experiments. It's always good because maybe. Nevertheless, so I think this is a very, very general issue with anything that has to do with probabilistic operations in a quantum system. Yeah, but any loss in imperfections in our experiments or our setups make operations probabilistic, and this probabilistic component in a long process creates usually exponential overhead. This way out is usually some kind of modification of this scheme of repeat until success to put it up in very small pieces, make the very small pieces, make it in a repeater success strategy, and then connect it together. So that's true for these two types of this quantum repeater, but it's also true for the linear optics quantum computation, which is based on this Kneel, Laflamme, and Milburn scheme, which came out roughly about the same time as the DLCZ scheme. And so these repeater success strategies are beautiful, but they become very cumbersome if you don't have perfect operations. And nevertheless, and any of these things, the key part is really to have a quantum memory. And an atom-like interface is probably one of the nicest and best way of getting you there.
So the previous, so the plot that you showed for the key generation rates in the previous slide, so that assumes perfect operations? Or?
No, that doesn't assume perfect operation. That assumes that assumes that you can have a quantum memory efficiency of 0.9, so 90% efficiency of your quantum memory, and 90% detection efficiency of your photons.
So efficiency of quantum memory is basically, that includes depolarization?
Yeah. So everything. You send the quantum state in there, what's the fidelity you get out?
So just so I understand, efficiency, is that different than fidelity in this case? Because fidelity of a half just means that it's gone. So.
Yeah, no. It's really efficiency
so it goes
of detection.
0 to 1.
It's 0 to 1. Yeah. So basically, if nothing comes out of the memory, if it's completely gone at 0.
Do you get tandem purification here? Because
that has
improve the efficiency.
No, but one of the thing is that what really makes this stuff so slow is that you need a lot of this entanglement purification, error correction, all the other stuff. That makes it, it makes these protocols very, very slow, because you need that, to do that, to be able to get a high fidelity parity. Yeah? That is exactly the problem.
Okay, so point 1 is the initial fidelity of the memory that you have.
Yeah.
Okay, and then you purify and then you obtain.
Yeah, they have to purify, and then they have to go through many steps, and if you do that, then you have to do, you probably have to send 10,000 of these qubits to get one that is with high fidelity in the end. So that's exactly what the problem is, that you need, these things are all, very, very beautiful concepts, but if you put them all together, things become, surprise. At least for us, this was a shock, yeah? That it's so hard, you know? We thought, okay, we do that, and you have to prove a little bit, and you get it there, because in the beginning it was thought that, you know, it sounded very, very reasonable, yeah? And in the end, it turned out to be. So I think in the end, quantum communication at long distances will not be much simpler than quantum computation. That's my gut feeling by now. But okay. So let's now check how to make a single atom single photon interface. Okay. I showed you this transparency before. So if you want to have a single atom as a single photon interacting with atoms, you can either use cavity QED, where you have and the photon interacting many, many times with a single atom, or you can use these collective states in ensembles, where you have many, many atoms interacting with a single photon. Yeah. Now, I will first of all concentrate on having a single photon with an atomic ensemble interacting, and show you a little bit about what was the original idea. So there's a feeling of this. The idea was the idea was you take a cell, a gas cell of rubidium, and you can use that as a quantum memory. And so the idea behind Peter Zollner's proposal was the following: you prepare, you have a three-level system that can be very easily done, for example, in this atom like rubidium or cesium or something like that. And you have two ground states and an excited state, and with optically pumping, you put everything in one of the ground states. To write an excitation in the system, you send a light pulse in that, with some probability, brings one excitation over to state number 2, and that is heralded. If this happens, it is heralded by sending a photon, a Stokes photon. Now, the Stokes photon is the one that I can send to somewhere else. The Stokes photon will tell me that, okay, I've created one excitation. And then, if this excitation, it basically means that this is some kind of a spin wave that you put in the system. Now, if I send another light beam in there, which goes now resonant, is near resonant to state 3 from 2, this allows you to pump this excitation over back to the state 1 and emits an anti-Stokes photon, and this anti-Stokes photon, because this is a spin wave as a momentum, this anti-Stokes photon is momentum correlated with the Stokes photon, and it's basically perfectly momentum correlated with the Stokes photon. As good as you really write it in. And you can see that there, because this process of writing creates this massive superposition state, which is basically, it's either the first of the atoms is in state 2, or the second of the atom is in state 2, or the third of the atom is in state 2, or the end of the atom is in state 2. And each of those states begets a phase factor, which is actually A delta K times R2, times the position where this is position, one, the first atom position, the second atom position, the third atom. So it gets this phase of that initial right beam will be written into the spin wave, and therefore also the anti-Stokes photon carries the phase of the read beam relative to the phase of the right beam, so they can be quantum correlated in there. So this was the beautiful way of also one of the key points of Peter's proposal, that you can take something, you get a photon out, which is the read beam, which tells you that I've created the excitation, and I can read the excitation out by sending another light in there. So the basic idea was, okay, you take an atomic ensemble, a cell, and you send in a read and a write light, and you will get Stokes and anti-Stokes light out, and they should be quantum correlated, because if I create one excitation, I read out one, and you should be able to violate the Cauchy-Schwarz inequality and all these other things with the system. Now, there's this ratio which basically tells you the second order correlation function between Stokes and anti-Stokes squared divided by the autocorrelation functions. That has to be smaller than 1 if it's classical. If it's larger than 1, you have a quantum correlation in the system. Now, people did experiments, and there was beautiful experiments by Misha done and by others, and we also did experiments, and we never got and nobody really got a very good violation of this ratio R. Now, from where does this come from? The basic problem is that in these cells, you have atoms, and these atoms, so that the atoms don't run around, you put them in a buffer gas cell. Everything is fine if your atom always stays in the ground state. But the read and write process brings your atoms in the excited state, and with the collisions between the gas atoms and the excited states destroy you. That type of quantum correlations. And we could show that in form of really spectroscopy measurements, that you see that if you don't have any collision, if you make the read-write process without collision in the excited state, you find very strong quantum correlations. If you take the systems when they collide up there, then at that other different frequency spectral range, you don't see them. So the problem was that anything that you confine your atoms in there with, now being that if this would be a ball or something like that, there's ideas of using fibers and things like that to do that. But you know, we said okay, then we get rid of this problem by making cold atoms. It took quite a while until people managed to circumvent that in a really nice way, and I think beautiful experiments for that are the ones from Ian Walmsley in Oxford, for example, where they use now picosecond pulses that are very, very fast, so that these processes are very fast in mobility, that during the time of this excitation, during the time of the Stokes and anti-Stokes processes, and a collision happens, becomes very, very small. So yeah, you see that you find that basically you find only that the quantum correlations exist only where the collision of the peak of the spectrum is where there's no collisions in there, and the other ones is gone. So you go to cold atoms. The experiment becomes much more complicated because you have to put, you know, what now here in between sits a cold atom setup instead of just a simple cell. But if you do that, you immediately get to this violation factor of 10 to the 6. Yeah? So you buy a lot of overhead of doing your experiment. It's not a so simple experiment anymore, but you can create the really nice quantum correlated photons out of this atomic ensemble. You can do that many, many times. You can show that there's a repeat of the success strategy. You can gain the rate more without losing the quantum correlations of the system. So that was nice to show, and there's beautiful experiments from Jeff Kimball in the same sense on that, where he also used cold atoms for doing that. Now, how to make create entanglement in a very efficient way? You take two of those ensembles, and you make one photon, and you write an excitation in system 1, and write an excitation in system 2. Yeah? And then afterwards you have written in excitation system 1 and excitation system 2. You both read them out simultaneously and send them on a beam splitter, and you get an homobundle interference. So you can make, in that sense, you can make a very high good probability of making a homobundle interference here, and then these emitted photons that come out there are not probabilistic anymore because you wrote them in before with this repeatedly success strategy, and then you can read them out and you get them. So this is one of the ways that people think that you can get rid of the problem to create very massively entangled states in photonic quantum computation. You do this not only with two, but you do it with many, many of these systems, and systems with this. So this is number one. Now you can show that you can make a homobundle tip with these experiments. You can show that these photons you can emit, you can create there, and you can violate Bell's inequality. So we really have, you know, you create an entangled photon pair. in there. And now it's more or less deterministic you create the entangled photon pair, compared to probabilistic in a dark conversion crystal. So this is what the quantum memory helps you to do that. Now, if you have an entanglement, what you can do, if you take inherited quantum memory, so you can say that I have now 2 of those ensembles, and if I take the photon out and put it on a polarizing beam splitter, I can create an entanglement between the U and the D atomic ensemble by then I have this photon, the polarization of this photon is then entangled with the state of these 2 atomic ensembles, and then I can do the following. I can take another photon, make a Bell state measurement, and teleport the quantum state of this photon into the atomic ensemble. So you can write a quantum memory. Yeah? Now things become much more complicated, and the other experiments take a few minutes. This experiment takes a day or something like that, because of statistics and all, it becomes much more complicated. But nevertheless, we can teleport a quantum state in there and show that it's really with a very high fidelity in teleporting quantum state. So that's how you write. You can teleport into a quantum memory. With this Bell state analyzer, you can basically make this type of measurements. Then you want to do this thing very robust. So basically, you don't want to put 2 different ensembles and make it very complicated. Then we tried the following thing, which in the first thing, then we thought we never ever would work. But in the end, it worked extremely well because the spin waves are so robust. You can think of that we said, let's try if we give the photons 2 possibilities to come out of the ensemble. And then you put these 2 photons together on the beam splitter with a halfway plate. So it means that if the photon comes out, the polarization of the R photon, yeah, is then right circular polarized, and the other photon is left circular polarized afterwards. I'm here, but I'm here. So I would have an entanglement between the k vector of the spin wave, which is correlated with the emission of the photon, and the polarization of the photon. Now the question was, if I read that out, do I get the 2 photons exactly on this momentum? If they are quantum correlated, they should come out. And it turns out that these 2 photons, you really find them in exactly the same momentum mode. We can put them together, and you can show that you can very highly violate Bell's inequalities with these photons that you created. And so you have basically a very simple qubit that you can make in such an atomic ensemble by just selecting the momentum modes of the photons that come out. Yeah? And that basically tells you that if I have a qubit now, I can implement this. I think to be able to implement then some of these other quantum repeater strategies. So, can we implement a quantum repeater node? There's one experiment by Jeff Kimball, who implemented this original DLZ repeater node, where he had 2 atomic ensembles which were the qubit, and sent in weak pulses, and by entangling these 2, by detecting only 1 photon, he could do exactly the repeater node from the one step of a repeater node from Peter Toller's idea, and then you do a second one. You do a Bell state measurement, and you read them out. You can see that you can basically make a type of entanglement creation. But here, this was very complicated because you had to really phase stabilize everything on there. If you take your atomic ensemble with the real qubit here, and not with a path entanglement, you can make the Bell state measurement between these two atomic ensembles, and they can send that through hundreds of meters of fibers which just lie around in the sun somewhere, and you still can create entanglement with very high fidelity, where you can show that these atoms that are sit here and here violate Bell's inequalities to a very high degree. Now, we can show that your entanglement thickness is very good, and so basically you have one part of such a node. Now the problem stays here. This experiment, to get that, was something like 2 months continuous data taking. Yeah, just to show. So it becomes really, really cumbersome, even though you have a repeated success strategy and everything. So things become very, 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 very complicated. So this was completely out of the question to go on there and build the large network. Yeah, it was nice to put these things together, and so we had to think about, can we make the quantum memory more efficient? Can we make the storage longer, or can look at different other systems to do that? So the first thing we did an experiment, also very naive. We thought about, okay, let's take this atomic ensemble, put it in a dipole trap, and then we get a long-term quantum memory. And it turns out, yeah, there are certain things you can do, which if you write in, if you want to do an atomic clock experiment, it can be very long time, very long storage time. But the quantum memory that we implemented there, the qubit there had a very short lifetime. Now we thought about, maybe it's magnetic fields, there's nothing on the problem. The problem was that these spin waves started to dephase because the atoms move, even if they are outer cold. Yeah? So the problem with the following is that if you want to do an efficient quantum memory, you have to separate the single heralding photons from the large read and write beams, which are 10 to the 12 times more intense than the single photons. So you usually have a very small angle between them. Now, if a very small angle between them, that basically means that these spin waves have different k vectors. And now, if each atom, I showed you in the superposition that in each atom has a specific phase written in there, and if these atoms now move, and so these phases start to become completely random. You see that if one of those atoms would move a different way, then if they move, then they get different phases, and so they completely randomize, and this spin wave starts to dephase because of the motion of the atoms, which was for us, in hindsight, it's trivial, yeah. But okay, then those experiments which were done there, 2 experiments with basically the same. They look like having the same first author, which is one from our group and one from Kutzwit's group. They were also both out, both of them. So that's just like, well, they were presentation physics in 2009. So it's yeah. So okay. We looked at this and we saw that depending on how big of an angle you have, you get a longer lifetime. We show that it's basically, it's really this dephasing of this motion of these atoms, because if you're completely longitudinal, if you would come out completely longitudinal, then the spin wave would have a very, very long wavelength, and then its dephasing would not be very bad. But because if you come out at a different angle, the spin wave had a shorter wavelength, which defines better your momentum and everything, but that's a faster. So we could measure that, and we could see that we get millisecond, we get some kind of a millisecond storage time if you get to t equals 0. Now, cavities can help interfacing between the atom and the light, and that's a beautiful experiment by the Bulletich group at MIT, where they showed that, even with a cavity, they could get very high read and write efficiency of an optical memory. And first they thought, okay, if you take a simple 2-level system, this would be the curves you would expect for a 2-level system. So you would get, if you have a read optical depth, which is something like 50, including the cavity helps you to get a very high optical depth. you should get, nearly perfect readout and write efficiencies, and in the end they never measured that. And it turns out the problem is that rubidium is not a two-level atom. Rubidium has, spin, has 3 plus 5 ground states and many excited states. And if you take all the coefficients in different, you find out that this is the thing you can get as best as you can get from these cavities. So the simple way of doing the storage, as we thought about, might not really work, because all of these ideas are built on very simple 2-level systems or 3-level systems, which are really nice, and they don't have any of these couplings that are on this side. Yeah. So I mean, here you get, it was 84%. Yeah, they got, and there's a similar experiment from Janway's group where they got efficiencies up to 80% read-write efficiencies, and looking at in the forward direction, looking at also millisecond storage times. That's beautiful experiments. We really want to do something with it. I think it will stop you very quick. It can maybe entangle 2, 3, 4, 5 these ensembles, but it cannot do more. Now the other idea is how you can make the way of how you can make the storage time much longer. The basic reason why this is that you have these different momenta create these spin waves that are tilted, and when the atoms move, they just basically destroy that. So what you can do is you can, let's put the atoms in the lattice. Then you find out that if you put it in the lattice, in a 2-level atom it will work nice. In a real atom it doesn't work nice. We have differential light shifts, and it's really difficult to get very long storage times, because otherwise the differential light shift would kill you. Except if you do the experiment with the Bose-Einstein condensate. If you do the experiment with the Bose-Einstein condensate, then you have repetition rates of best of a second. These other experiments, all I showed you, they always have repetition rates of 100,000 tries per second. Yeah, because you can do it with an atomic ensemble, and then everything gets very fast. If you do it with the Bose-Einstein condensate, forget it. You lose the rate. Nevertheless, so it basically means that by finding very simple dipole traps and going very far into something, you don't really find something. So you need some very clever design of traps and stuff like that. And so what did people do? There was a beautiful experiment where Kutzwitsch put in things in a spin wave in an optical lattice, and then there was this beautiful experiment by Immanuel Bloch, who showed that you can store light for 600 milliseconds in a Bose-Einstein condensate trapped in an optical lattice. And so, in principle, there are ways around it, but it's difficult, and it's not really practical if you want to use it really for doing this hybrid type of system experiments. And then we thought about, in these traps of thinking of, can you make dark states that really clock states that compensate all the light shifts and the magnetic states. And we didn't find it, but there was a guy called Delvianko, and I think this paper was never ever published. It's only in the archive. And it's a Russian atomic physics theorist who works, I think, in Reno or somewhere, who figured out that
he was an ITAMP postdoc.
He was an ITAMP postdoc then?
And he's in Reno.
What?
Yes. He's in Reno.
He's in Reno, yeah. And so he figured out that, okay, if you take a certain magnetic field and a certain polarization of the light and a certain polarization of the trapping light, you get a clock state. And Kutzwitsch did then an experiment which showed that if you hit the right magnetic field light polarization, you get the storage time very, very long. And now his latest experiments from last year, I think, or 2 years ago, showed that you have a storage time of 20 seconds. In the order of 20 seconds. So there are ways around, but they sometimes are not very simple. But it's also, I don't know see, the storage efficiency here is very small. I don't know if you can combine this with the storage efficiency that's again, you know, at 80%. It's usually things that you achieve in one experiment that, and the other experiment you achieve that. So you
Why is the storage efficiency small here?
I don't know on this experiment. I didn't. I was so frustrated that time, I have to tell you, that I dropped doing the work with these atomic ensembles in 2008, 2009, because I thought, you know, okay, there's a limit, and I didn't, you know, we tried to find it, and, you know, at least I was, you know, not good enough trained in atomic physics to figure that out. And I think that's a really very clever and important paper. Did he do that in ITAMP or?
No, it is botanics.
There's gone, okay, yeah. So in the end, you can think of putting something, making a qubit, I think, where you take some kind of rubidium cesium cloud and you put everything on fibers on some kind of a chip, and then have these spin waves with the correct magnetic fields and make it a really nice storage medium where you can basically have your qubit we connect with fibers to it. So in principle, I think it's possible. This is a plot of one of my very, very old grad applications, which are completely shelved away, which I thought was never going to be able to work now. But now, I think, you know, if you really work hard on it, you could do that. I think what's much more promising, and which is the things that Arnold Oschenbeutel does, where he now really works with you can also get very strong interaction between the light field and the atoms when you go to extremely thin fibers, where most of the light field is outside. We can trap an atom very close to such a fiber. You can get very, very high coupling strength between an atom or a molecule, in fact, and the fiber, or a quantum dot or whatever you want in the fiber. And what is amazing is that he can make these things in such a way that the transmission from here to here is 99%. Yeah. So basically, this really tells you can wire up this type of systems using these fibers. And you know, he did a lot of experiments on understanding this interaction between the atoms and these very funny properties of this field, which is half trapped and half open. And there were just a few nice papers about, you know, chiral photons and things like this and so I think you will see a lot of stuff, and then if this is understood, you can think about using that in coupling two atoms for a quantum memory. I think that's a nice way. He was able to switch a photon with another photon and stuff like that using this type of experiment. So this was the atomic ensembles. It's fun, it's nice physics, but it's probably, you know, hard if you want to go further. The other part is that take a cavity, and if you take a cavity and hold an atom in the cavity in there, like in a dipole trap, you can excite the atom there. I can use this atom, and these are experiments now from Rempe's group. There are similar ones from other cavity QED groups, but I think they're ones from Rempe. They just fit nicely and give a nice story here. So you can have a single photon. You can grade that. You can take an atom there. You can put you hold it. You can hold this atom for tens of seconds in the cavity, and then you excite the atom with a trigger, and then it emits a photon, and then you take it back, and so you excite the atom, it emits a photon, it comes out there, and there's a single photon. It's a single photon source. Then you have to go. You put it back in your state, you cool it, and then you trigger it again. And so basically, they showed that they could take, use an atom for 28 seconds. You get about 10 to the 5 single photons out, and you detect about 11% of that. So it basically tells you this is a single photon source. It's not quite on demand, but it's pretty good on demand. Yeah. Now people learn to do very similar things now with quantum dots, and you can make very high efficiency of quantum dots. But the problem is that in quantum dot, the photons are not identical. Are not perfectly identical. These photons are perfectly identical. Now you can go further, and you can entangle that photon, with this atom with the photon that comes out there, if you want to get a quantum connection between the atom in the cavity and the photon. This is by using different sets of, making very similar experiments, using now, but using different, preparing the atoms in very specific states and using specific lights to entangle them, so you can basically take, put the atom in the M equals 0 state, take a pi photon up and observe sigma minus and sigma plus photons down there, because from here to here, this is forbidden, so it has to go to sigma plus or sigma minus, and then the atomic state and the photon polarization is entangled, and then you can put again a pi light on there, and you can get a map readout of the photon, and so basically you could show that with very high fidelity that the atom, so that this photon and this photon after the mapping were entangled, so the photon and the atom had to be entangled. So this is how you make an entanglement now between an atom and photon. This you could use now to teleport something into the atom. Yeah? And the final stuff is that they also managed to write something into the atom. So you remember there was this beautiful graph that Paula showed you for the quantum internet. So you have to get something out, but you also have to get something in all of these proposals. And here they basically show that you can basically write a quantum state into an atom, but here you see again a problem. This is the input pulse you want to write in. You have your control field that allows you to switch the photon over into the atomic state with a Raman transition, but nevertheless you find that something 50% of the photon gets. And then after some time you read out, and it's not perfectly exactly the same shape, but nevertheless, they get a quantum fidelity which is above classical, over something like typically 100 microseconds. And so now you have all these things you can write in, read out, and now we have to put these things together. And I think Gerd managed to do also experiments where he entangled two cavities with atoms and stuff like this. There's similar sets of experiments that people want to use that. We'll have an ion in there, in a cavity, and so there are many sets of this type of experiments. Now, atoms are nice, but it would be much better if you don't have to make a big optical table for these type of things, but just you can put a diamond or some crystal or something in there, instead of really using this whole overhead of an atomic physics experiment. And the idea basically is that you take some kind of solid state atom. The atoms are identical quantum objects. Single atom is a single photon emitter. Its interactions are known. I think with atomic physics you have the ultimate precision in physics that you can achieve. And atoms move in free space, but you need to cool them, to trap them. So you need a huge overhead that you have here. But in a solid state, there's a big variety of emitters. There are ions in solids, there are defects in diamonds. There are many atoms like quantum dots and many other things. Each of those things, you make them, you can fabricate them, you can put them somewhere and it stays there. Hopefully, except, sometimes they bleach, or sometimes some of these things bleach, some of these things, happen, Sometimes ionize, and we send us ionize, which they do, which is a pain. Yeah.
They do. Sometimes people say they don't.
Yeah, but they do. It's a pain. Yeah, it's a real pain. Yeah. So take this with a grain of salt. But they are very strongly influenced by the matrix, and they have strongly homogeneous problem if you use this ensembles. So what people thought about is that, hey, and this goes back to or I think original work is from Stefan Kroll in Lund, but Niklas Jusin's group in Geneva did a lot of work, and they had this really nice idea that you can write a frequency comb into the system, and then if you write, you can write many different frequency combs into the system, and that allows you to store in this broad, which is broadly many quantum states, and so the basic idea in the beginning was you have a ground state, you have an excited state, and you have an input mode, and because of, if you write different frequencies in there, they will dephase, the system would stay in there, but they will, if their frequencies are all commensurate, it would come out after rephasing time. Now you can take this, put it in an auxiliary state, store it there, and then put it back and put it into an optical transition. And so you should have, you put something in, you wait, you put it into your optical. If you don't put it in an optical state, you put something in and it comes out. If you put it in a storage state in between, you put it in, it stays there and it comes out. So in principle, this should work, but it's a very difficult system to find the right crystals and things like that. Nevertheless, Nicolas Fissard and also the group in Calgary from Wolfgang Tittel managed to do, use something like, there are many crystals. One example is in neodymium ions in an YBO4 crystal, yttrium vanadium oxide crystal. And they write in, they prepare their frequency comb by not by the frequency, by making pulses, which gives you in the frequency domain something, and so you can read in something, and you can find it, you can write out, you can show that it's coherent storage, but the efficiencies are not very high in the beginning. Nevertheless, I think you can see this, you can store these things, and people have now done that in waveguides. People have done that in many different other systems. So you can really store weak. So what people did, they stored weak coherent pulses. I think nobody ever stored a single photon pulse in there, really, but it's in some senses. So in the end, I know what's the time. I have a few minutes. So there's basically what we can think of doing. We can also use the idea would be not to use an ensemble, but to use a single electron spin as a quantum memory, or a single nuclear spin as a quantum memory. And this is something that we're building up, and we try to do. And it's basically based on the following idea: is that you put an NV center in a cavity, and if you put this NV center in a cavity, the cavity talks to the optical transitions, and if you do that right, you can probe the quantum state of the NV center by reflecting light of the cavity, because if the cavity is resonant with one of these transitions but not with the other one, it will be the photon will be reflected if it's in state 1, and it will be absorbed by the cavity if it's in state 0. Now we can make a measurement of the quantum state in there, and if you go on that, you can think about what is if I take two NV centers in cavities, prepare them as each of them in a superposition state between state 0 and 1, and then send a single photon on there. And if I detect the photon here, if and only if I detect the photon here, I project these two NV centers in that entangled state. And this photon never ever interacted with the NV center. So it can't do anything stupid with all these excited states that are in there. Yeah? Because if I send a single photon in there and detect it, I know that I've projected them onto them. This is not a perfect way of making an entanglement. Its success probability is only 12.5%. But nevertheless, I can, the question is that can you use that way of creating, so to speak, an entanglement between, using the photon now to create an entanglement between different states. In fact, you can use that to do that over a fiber, and then you could use that creating entanglement over large distances. And so you can start taking this entanglement, writing them into the nuclear spin, which would be I can basically use the nitrogen 15 spin as a nuclear memory, because then if you never excite the spin, then it's not a problem. Usually, the nitrogen spin makes a problem if the NV center gets excited. So basically, what we build together a complete architecture where the NV center never ever gets excited because it sits in the cavity, and so you can go and build large structures, cluster states, and that's it all in there, that paper in there, and this is where I said build a topological gate. You can find out how you do that, and in the end you get to a regime where you find that you can get, if you can do all the operations better than 99.3%, you would be below, you could be better than this threshold of fault tolerance you can make error correction. And we try to take the best, try to take the published data on the NV centers. These are, this would be the threshold, and this is what is known now, and this is what I think one can achieve. So I think in principle this is an architecture from the way that we know now that can be used, and it's not probabilistic in the creation because it uses the spin of the nitrogen and not the spin of the carbon that's nearby. So that's the good news. The bad news is that it takes a huge overhead. That's what I said. If you want to do a calculation, you need 10 to the 10 of those, yeah, which is really bad. You can do that. You can get very good logical error rates and everything, but it's slow, yeah. So one logical operation time would take 14 milliseconds, and it's limited by the time to manipulate the nuclear spin. It's limited to the time it takes to detect the electron spin within the cavity. And you can do the same architecture using a quantum repeater. And so I think this is some kind of a combination. You try to put a solid state spin into one of these cavities and hope to do that. I don't know, it will take another 10 years to build something like that. So to be realistic, you have to, what we are learning now is to do these things in such a way that the NV centers, when do they ionize, what do we do, how do we probe them, and there's many different things, and how do we fabricate these things, how do we put them, and what we are able to fabricate an area of 10 independently tunable cavities where you can put things in there, and they can hold them. So that's at least we know you can build something like that, and it's always nice to have work and things you can show a device where in principle you could do something like that with it in there. I think these are cavities that Michael Tuke does that, and so he built with the cavities that he built for his PhD in Imperial College. It should at least work to tackle a few of those. So let's see. It will take a few more years to do that. I think that gives me to an end, and thank you for listening. And I think on Saturday evening is at my course.
Thank you.
Frustrated now because I said that everything is so hard, it doesn't work. It's fun to do. It's really fun to do. Yeah. But keep the theorists and ask them the questions that what happens if this is not the efficiency one, if it's not different. This is the
Okay, we have time for a few questions, but is dinner ready? Is it warm or cold, or is it the souffle tonight?
It is El Charro, authentic Sonoran Mexican food tonight.
Oh, that would be cool. But I think we should take time for a few questions, and you should not be discouraged, okay?
No.
You should still continue your studies, okay? I don't want to see people say, I quit.
No. I don't think that's, but I think it's also don't be frustrated if things don't work, They never work, but you can do a lot.
But these guys need to get a PhD.
Yeah, but there are many people that are interested with these things,
All right, anyway, questions? Comments? Criticism? Yeah.
How rapidly can you read out the nuclear spin in the NV center?
How
quickly can you read the nuclear
Oh, you have to put in, you have to write, connect the nuclear spin to the electron spin, and then so it takes you to the transfer to the electron spin, and then you have to read the electron spin.
So you
To get the efficiency, you cannot do, to get to the, if you do single shot, an efficiency of bits is something like 85%, so you have to redo it once or twice. Yeah.
Well, it depends. If you can apply Tesla, you can get up to 9
Yeah.
or something like that.
No, but no, you read it out to the cavity. Read it out a reflection of the cavity.
Oh, okay.
Because we don't want,
So you're not doing any fluorescence?
yeah, we don't, it never, if a photon is lost, we reset it and start on that center for you. So that's a question because you don't get into any of these uncontrolled, the question was, there's lots of uncontrollable things if the photon gets in, and that's a problem.
So if you're not using fluorescence, why do you care to use NV filters? I mean, why not go to silicon? Because
Maybe.
it's cleaner.
Maybe it would be much nicer to do that, yes, but yeah. But the thing is that on NBC there were all the data on there. So we basically say you can use this type of idea, rocket, with any of these defects. But you have to know, we wanted to do it and see, this is the best known. It's also the easiest one to work with, where you can play with, if you start,
Yeah.
you start play with it.
You have an orthogonal readout as well if you decide to check.
Yes, you can check things and everything. I think you can dig in a lot of other technology, which is on the side, and you know how to do them. There's many things to learn. If you start with a completely new system and you don't see anything, you don't know what is. If you know that a certain architecture works and how to do it, then you can swap in a different one and see if things work. If you learn it. That's the philosophy behind that. And of course, if somebody comes up, there's probably much better for certain type of architecture, much better centers. But I mean, there's one which we know most of it, or many things of it.
So if I have to do one out of purification, so suppose if I have to apply sigma gate,
Yeah.
if you have atomic ensembles, you use the linear optics to do a sigma
Yes.
gate, which is limited to the maximum efficiency of half.
Yeah.
Right, so that's going to be a limited efficiency for atomic ensembles.
Yes, that's.
On the other hand, if you have ions, you can have a sigma gate with 99.999% efficiency.
Yes.
But on the other hand, it's harder to couple them down to a
Yes. Yes. So these calculations that were done from Nicholas Design School, there were 4 atomic. This is basically atomic ensembles. So this. Of course, if you can have better system, that's a huge motivation. For instance, from Rainer Blah, to couple, ions to their photons and things like this. So also in a repeater with the NV centers, you can once entangle electron spin, put it in nuclear spin, and entangle electron spin again, and then you can do the connection. Many of these operations with unit efficiency, and that's also the idea behind it. So, but we see. Let's go again.
Okay, thanks again.